Good day. We hope you are all safe and healthy. Kung medyo mahina, pwedeng pakilakas na lang ng konti yung volume. So today's lecture will be a review of functions. If you want to take down notes, you can pause the video and continue playing after you have taken down notes. So this is the outline for today's lecture. First, we consider function as a pairing. Then, we proceed to the variable y as a function of x. Then, we get values of a function. Then, we find the domain of a function and do some operations on functions. We first proceed with function as a pairing. Recall that a function from a set A to a set B is a rule where each element x of A is paired with exactly one element y of B. For example, let A be the set of real numbers and B be the set of real numbers. Consider the rule F where each x in A is paired with y equals x squared. If x equals 1, then y equals 1 squared equals 1. So for x equals 1, we get one value of y. If x equals 3, then y equals 3 squared equals 9. So if x equals 3, we get one value of y. If x equals negative 1, then y is the square of negative 1, which is 1. So if x equals negative 1, we get one value of y. If x equals 1/2, then y equals 1/2 squared equals 1/4. So if x equals 1/2, we compute for one value of y. And so on. Although we cannot get all the possible values of x, we can say that in principle, that every time we specify a value for x, we get exactly one value of y for this value of x. So that f is a function from A to B. To consider this function as a pairing, suppose this is the set A and this is the set B. Then f pairs 1 with 1, 3 with 9, negative 1 with 1, and 1/2 with 1/4, and so on. Notice that 1 and negative 1 are paired with the same element of the set B. And it is possible for a function that two different values of x are paired with the same value of y. Let me mention some remarks. We also denote by this symbol if f is a function from A to B. Also, a function from A to B can be viewed as a set of ordered pairs, such that two different ordered pairs are not allowed to have the same value of x. We proceed with the variable y as a function of x. Given an equation in x and y, then we say that y is a function of x if each value of x in R gives at most one value of y in R from the equation. For example, consider the equation y equals x squared. Then, as we have discussed earlier, If we specify a value of x, then we get one value of y for that particular value of x. In other words, for each value of x in R, we get exactly one value of y in R, so that y is a function of x. Let's have some examples. Is y a function of x given the equation x plus y equals 1? To answer this, we express y in terms of x. If x plus y equals 1, then y equals 1 minus x. In this case, for each value of x in R, we get exactly one value of y in R, so that y is a function of x. Let's have another example. Given the equation x squared plus y squared equals 4, is y a function of x? To answer this, we try to express y in terms of x. If x squared plus y squared equals 4, then y squared equals 4 minus x squared, so that y equals plus or minus square root of 4 minus x squared. This suggests that we can have a value of x for which we can compute for two values of y for this value of x. Now, if x equals 0, then y equals plus or minus square root of 4, which means that y equals 2 or y equals negative 2. So for some value of x, we get more than one value of y. So y is not a function of x. Okay. Another example. What if absolute of y is equal to x plus 2? Is y a function of x? Observe that if x equals 1, then the absolute value of y is equal to 1 plus 2, which is 3. And there are two real numbers where the absolute value is 3. Y equals 3 or y equals negative 3. So for some value of x, we get more than one value of y, so that y is not a function of x. If you have any questions, you may ask your teacher. So let's proceed with finding the value of a function. If f pairs x with y, we say that y equals f of x. We go back to our very first example. Let f be the function where each x in A is paired with y equals x squared. Since x is paired with y equals x squared, then f of x equals x squared. Now f of 1, we just replace x in the equation f of x equals x squared by 1. So f of 1 equals 1 squared equals 1. F of 3 equals 3 squared equals 9. F of negative 1 is the square of negative 1, which is 1. F of 1/2 is equal to 1/2 squared, which is equal to 1/4. Let's have another example. Let f be a function such that f of x equals x squared for every x in R. If h is in R with h is not equal to 0, simplify the expression f of x plus h minus f of x over h. To simplify this expression, we first find f of x plus h. To find that, we replace x in the equation. F of x equals x squared by x plus h. So f of x plus h equals x plus h squared. Then we subtract f of x, which is x squared, and then we divide by h. Now, x plus h squared equals x squared plus 2xh plus h squared. And then we copy the rest of the expression. We can cancel out x squared in the numerator so that we have 2xh plus h squared over h. And we divide the numerator by the denominator to get 2x plus h. This is now the simplified expression. Okay. We now proceed with finding the domain of a function. Let f be a function from a to b. The set A is called the domain of f, denoted by dom f. The set of all resulting values of f of x, where x is in A, is called the range of f, denoted by ran f. Let's go back to our very first example. Let f be the function such that f of x equals x squared. The domain of f is just the set A, which is equal to R. Now, the range of f is the set of all resulting values of f of x. But when x is a real number, x squared must always be greater than or equal to 0. So the range of f is the interval 0 to infinity. We can define a function in the form f of x equals some expression in x, where the domain of f is the set of all real numbers x, such that f of x is also a real number. If x is in the domain of f, we say that f is defined at x. To find the domain of this function f, since f must be defined at x, we will not include the values of x that make the denominator 0 and the values of x that make the radicand negative when the index of the radical is even. So let's have some examples. Find the domain of the function f of x equals x plus 1 over x squared minus 3x. If x squared minus 3x equals 0, then x times x minus 3 equals 0. So x equals 0 or x equals 3. Since the denominator must not be 0, the domain of f is the set of real numbers x such that x squared minus 3x is not equal to 0. Since 0 and 3 are the values of x for which the denominator is 0, we can write this set in this form, which is also equal to the set R not including 0 and 3. Next, find the domain of the function f of x equals square root of 1 minus 4x. Since we have a square root, then the index of the radical is equal to 2, which is even. So the expression inside, which is 1 minus 4x, must not be negative. So that 1 minus 4x is greater than or equal to 0. Adding 4x to both sides, we get 1 is greater than or equal to 4x. Dividing both sides by 4, we get 1/4 is greater than or equal to x, since 4 is positive. Or, x is less than or equal to 1/4. So the domain of f is the set of all x where 1 minus 4x is greater than or equal to 0. So if this is true, then x is less than or equal to 1/4. So the domain is the interval negative infinity to 1/4. Okay? How about f of x equals cube root of 1 minus 4x? Since the index of the radical is equal to 3, which is odd, then even if the expression inside is negative, f of x is still defined. As long as the expression inside the radical is defined, so the domain of f is the set of all x such that 1 minus 4x is a real number, this is just the set of real numbers. Since for every x, 1 minus 4x is defined. We hope you can see the difference of this example from the previous example with the square root. Okay. Next, we find the domain of the function f of x equals 3 minus square root of x plus 5 over x plus 1. For x to be in the domain of f, the denominator must not be 0. So x plus 1 is not equal to 0. At the same time, x plus 5 or the expression inside the square root must be greater than or equal to 0. So the domain of f is the set of all x such that x plus 1 is not equal to 0 intersect with the set of all x such that x plus 5 is greater than or equal to 0. We get the intersection because we want to find all x such that this and this happen at the same time. If x plus 1 is not equal to 0, then x is not equal to negative 1. So the first set here is equal to r not including negative 1. We intersect with this set. If x plus 5 is greater than or equal to 0, then x is greater than or equal to negative 5. So this set is the interval negative 5 to infinity. We can write this intersection in this form. Negative 5 to infinity, not including negative 1. Next, find the domain of the function f of x equals square root of x squared minus 4x plus 3. Again, we have a square root, so the expression inside the square root must be greater than or equal to 0. We find the solution set of this inequality. So, we factor out the expression in the left-hand side. x minus 1 times x minus 3 is greater than or equal to 0. Now, for this inequality, we find the critical numbers or the numbers x for which the expression in the left-hand side is equal to 0. So, the critical numbers are 1 and 3. From the critical numbers, we construct a table of signs as follows. The columns here are the intervals, and the rows here are the factors of this expression and the product. We now fill in the table of signs. X minus 1 is negative when x is less than 1. So if x is in the interval negative infinity to 1, negative cx minus 1. X minus 1 is positive when x is greater than 1. So if x is in the interval 1 to 3, 3 to infinity, positive cx minus 1. Okay? Now, for x minus 3, it is negative when x is less than 3 and positive when x is greater than 3. We now determine the sign of the product. When x is in this interval, negative times negative, so the product is positive. When x is in this interval, positive times negative is negative. When x is in this interval, positive times positive is positive. So, we should get all the intervals where the product is greater than or equal to 0. So that all x in the interval negative infinity to 1, open, union, open, 3 to infinity, are in the domain of f. But we are not yet finished because we have to check if the critical numbers satisfy this inequality. If we substitute x equals 1 here, then the left-hand side is 0. And it is true that 0 is greater than or equal to 0. So, kasali yung 1. If x equals 3, then the left-hand side is also 0. And it is true that 0 is greater than or equal to 0. So, kasali din yung 3. So that 1 and 3 are in the domain of f. So, combining these values and these values, the domain of f is this interval, negative infinity to 1, closed, union, closed, 3 to infinity. Okay? If you have any questions, you can ask your teacher.